Hello, and welcome to Coding with Kriller. Today I'm going to be discussing how to do math with Arduino. By the end of this lesson, you should be able to use math to do a lot of fun stuff with the Teensy's onboard LED. However, this is hardly all that you can use math for. After next week's video, when I plan to discuss the serial port and serial printing, you should be able to do a great deal more, writing applications that allow you to calculate whatever you want based on any inputs you give. You'll also be able to code some Mad Libs games and other fun activities, but those aren't the subject at hand. For now, let's focus on math and get on with the video. When you think of math, you may think of a lot of complicated operations, such as trigonometry or logarithms. While this is something the Teensy can do, and I will probably make a video on it in the future, that math isn't necessary for most code you will be writing. That's why this video will focus on more basic math such as addition, subtraction, and exponents. And speaking of basic math, it's time to look at the most basic part of math of all. The equal sign is so ubiquitous in math that we often forget it even exists. We all know what it means. The stuff on the left of the equation is equal to the stuff on the right. However, it means something different in C++, which leaves us with weird equations like this. Now we all know that this makes no sense as a normal equation. Something can't equal itself plus 1. However, it makes sense when you consider that the equal sign in C++ doesn't mean that something is equal to something else, but rather sets something as equal to something else. In this scenario, the processor takes the number held by example variable, adds 1 to that value, and then puts the new value in example variable. This is how all equations work in C++. The processor does all of the math on the right side and fills the variable on the left side with whichever number it has found. This is also why any equations you write in C++ need to have the left side consisting of only one variable and nothing else. Equations like this won't work because the left side is much too complicated for the processor to understand. Now that we have the basic meaning of the equal sign out of the way, let's move on to actual math. Addition, subtraction, multiplication, and division in Arduino are all relatively simple. You take a value, be it a number or a variable containing a number, write the necessary sign, and then write the other value used in the equation. While you can see that the processor doesn't really care how many spaces you use, I highly recommend using one space because it makes it much easier to read. Also remember to always put a semicolon at the end of every line. Now that we have this basic math down, let's look at exponents. The first function I want to address is the square root function. The processor will take the value of any function you put in the parentheses and output the square root of that value, as long as the value is a positive number. You can even find the square root of a fraction, as long as the fraction is positive. The thing about the square root function is that all it can do is find the square root of a number. For all the other times you need to do exponentiation, you need to use the power function. The power function works by taking whatever value you have entered before the comma and raising it to the power of the value entered after the comma. The first value can be a positive whole number, a fraction, or even a negative number. The second value can be a positive number, a negative number, or even a fraction as well. That said, if the first number is negative, the second number must have an integer value. Just like you can't find the square root of a negative number, the processor won't let you find any root of a negative number, even if it has a value that should make sense. It's annoying, but computers aren't people, and we need to get used to it. Finally, one last thing to note about the power function before I move on. When using fractional exponents, always make sure to leave the fraction as a division problem instead of a decimal. And make sure to always put a decimal point and a 0 after both the numerator and denominator. If you forget either of these rules, the power function may give you an incorrect value for your answer. Now it's time to talk order of operations, or Pemdas. Pemdas stands for parentheses, exponents, multiplication and division, and addition and subtraction. This is the order in which the processor performs all of the operations in any equation. First, the processor treats anything inside a pair of parentheses like a mini equation and solves it. Then it solves any value set to an exponent. After that, it solves for all values being multiplied or divided. Finally, it solves for values being added or subtracted. This image is an example of Pemdas. The division will take place first, giving a value of 1. Then it will be added to 2, leaving us with a value of 3. On the other hand, in this equation, the addition inside the parentheses will be performed first, leaving us with a value of 4 before being divided by 2, leaving us with a value of 2. While the difference between 2 and 3 isn't much, the difference between a correctly and incorrectly written equation can grow very large once you start to write more complicated equations. Make sure to remember to use Pemdas. Now that we understand how to do basic math, it's time to discuss a very important difference that may completely ruin any equations you write if you forget it. The difference between integers and floats. You see, only variables of the floating point data type or double precision floating point data type can hold decimals. If you use integer variables in any of your equations, be it on the left or right-hand side, you run the risk of the processor cutting out the decimals, giving you an incorrect answer. This is also why you need to put a decimal point and 0 after all of the numbers you use, because if you don't do this, the processor will run the calculation as if the numbers are integer variables. For example, in this equation, even though example variable is declared as a float, the numbers 1 and 2 aren't, so the final answer is 0. This is because the processor takes the answer of 0.5, lops off the data after the decimal point to make it an integer, and then converts it to a float. Make sure to always use floating point variables and numbers with decimals to prevent this from happening. If you do need to put your final answer in an integer variable for some reason, it is best to use the round function. Since integers just lop off any number after the decimal point, converting to an integer always rounds down. For example, a number such as 0.5 would be rounded to 0, which is much too low. On the other hand, the round function would apply the rules of rounding, and round up for any value greater than or equal to 0.5. In this scenario, it will give us a value of 1. While integers may be horrible to do math with, there is one case where they shine. This is the modulo function. When you divide two integers and replace the division sign with the percentage sign, you get the modulo function. Instead of dividing one integer by the other, this function finds the remainder. For example, in this scenario, the remainder is 1. That said, I still have to teach you about one last type of function that I couldn't teach you about in the last video, and I personally think that the modulo function looks dumb. That's why we're about to build our own. The first thing to know is that not all functions are void functions. Void functions get their name because they don't return any data. Their data type is void. However, you can code functions to return all sorts of data. The modulo function will return an integer value, so we will use the keyword int to denote its data type. Because division requires two numbers, we will give the modulo diy function two parameters, int a and int b. Inside the function, we will create the variables int temp variable and int remainder. First, we will set temp variable equal to a over b. Because all of the values involved are integers, the result should exclude anything after the decimal. Then we will set temp variable equal to its current value times b. This equation would set it equal to a if this were normal math, but because the microcontroller is using integers to do math, the part of the number after the decimal point has been lost and will not be multiplied by b and remain part of the value in temp variable. Now that temp variable is holding all of a except the part that couldn't be neatly divided, we can say it holds a minus the remainder. By subtracting this value from a, we then get the remainder. Finally, we use the return keyword next to the remainder variable to set the value of the entire modulo diy function equal to the remainder and return it to the call. But what is the call, you may be wondering? Previously, we have simply called a function and let anything inside of it run before moving on to the next line in the loop or other function from which it was called. If this is the case, what are we returning the value of the modulo diy function to? One of the cool things about non-void functions is that we place their call in equations. For example, for the modulo diy function, we can put its value in the variable int z and make its arguments whatever integer values we want. In this case, I have done 10 and 3. Of course, now that the modulo diy function has been created, you can copy and paste it into new sketches if you want to use it again, and use it in whatever equation you need to. That's one of the fun things about functions. Not only do they help you organize and control your code, but they are extremely versatile and reusable. Now that you know how to do math on your Teensy, you may be itching to try it out. Unfortunately, until I cover serial printing next week, you can't do a ton of stuff. That said, there are some things you can do. For example, you can make your light blink with a delay that becomes bigger or smaller with every time the loop runs. To do this, declare the delay as a global variable, and then add in an equation that changes the value of the delay with each cycle of the loop. If you want to make your code look professional, you can use incrementation, which is where you write the variable, the operation you want to use, the equal sign, and then the value you want to perform this operation with. For example, blink delay is multiplied by 2 each time this equation runs. You can also use plus plus and minus minus, but these only add or subtract 1 each time, and a 1 millisecond difference in the delay won't be that noticeable. I hope this tutorial on doing math in C++ has helped, and I am super pumped for my next video, which should really open the door for a bunch more fun coding. Until then, have a great day. Okay, time for this week's charity shoutout. With all of the crazy events happening recently, I thought I'd take a moment to ask you to donate to the ACLU. Although recently, they've been focused on fighting unconstitutional practices and civil liberty violations by certain police departments, they also fight for the civil liberties of Americans in a wide variety of areas. If you would like to make a donation, simply go to their site and donate.